All right, let's get started here. It's 2:30. So small class, I think it's last class before spring break. So all of you get bonus points for coming, all right? So we will continue from where we left off last time. Just as a recap, we were talking about this notion of clock synchronization, and we talked about physical clocks, synchronizing physical clocks. Then I started discussing this notion of a logical clock, which is basically an integer that captures key events in a process. The clock only ticks when an event occurs, unlike a physical clock that ticks every second. So you're capturing events, and those events get timestamped. And we want to essentially synchronize processes using message passing. Okay? So essentially, when a message is sent, you send the clock value with it. And then when the message is received, you take the clock value of the remote process, your local clock value, max of the 2 plus 1. Okay? What this allows us to do is it allows us to essentially get that property which says that if A and B are two events you care about, and you know that A happened before B, then the timestamp or the clock value you assigned to A is going to be less than the clock value you assigned to B. Okay. And if A and B are concurrent events, then we don't care what the clock values are. Okay? And then the example I showed at the very end was, here are three processes. The numbers there are the logical clock values, which is just integers. And then as you can see, if you want to maintain the happened before relationship, the main property we are using is the sending of a message happened before the receive. You cannot send a message before it's received. So here is a message that's sent. The clock value at that process is 60. When the message is received, the clock value is 56 on that other local process. So clearly here, if you don't do something about this clock value, you will see that the receive event has gotten a lower clock value than the send. So if you take the max of the clock on the remote process and this one plus 1, you will adjust that to 61 rather than 56. So this is going to ensure that your happened before relationship is maintained. Okay. Now, the property that we want is not just that one, which is if A happened before B, then the timestamp of A is less than timestamp of B, but we want the reverse property also. We want to take two timestamps. You want to compare them and say what order did the events occur. Okay? This is what you do with physical clocks. You timestamp files, you timestamp events, and looking at the time values, you can say, okay, this has a lower timestamp than the other. So this must have happened before the other event. So that's what we do with physical clocks. We want the same property with logical clocks, except that Lamport's clock is only giving us half of the solution, which is if A happened before B, it's guaranteeing that the timestamp of A is less than timestamp of B. But we want that to go, implication to go in the both direction. We also, in addition to this, we want if the timestamp of A is less than the timestamp of B, we want to be able to say that A happened before B just by looking at that timestamp. Okay? So we will now look at an extension of Lamport's or logical clocks, which are called vector clocks. Just to keep in mind, the technique I talked about here is either referred to as logical clocks, or they're also referred to as Lamport's clock, based on the Leslie Lamport, who originally proposed them. Okay, so you will hear both of these terms; they mean the same thing. Okay, so now let's look at vector clocks. But before we do that, I just want to mention maybe a couple small things, which is in Lamport's clocks or logical clocks, when you have two events that are concurrent, you cannot assign an order to them. Okay, so for example, we have some events there which are before the sending of any message. There is no ordering defined because there's no happened before relationship. Okay, so you only get a partial order using logical clocks. Okay? Now, if you want to randomly decide an order, you can do that. Okay? Because some events are ordered based on the sending and receiving of messages, but there are many events that are not ordered at all. Okay? In particular, anything after the send or anything before the receive are not ordered. So if you want to order them, what you can do is you can impose some additional rules that just determines an arbitrary order for concurrent event. That doesn't necessarily mean that the events occurred in a particular order, but you just get some order. Okay? And the way we do this is we essentially take the logical clock integer, okay, and then attach the process ID to it. Okay, so here 1.1 essentially says the logical clock value is the 1, 2, 3, and so on, and then you essentially make it a decimal notation, and then you attach the process ID, in which case it's 1. Okay, so 1.1 essentially means that's event 1 on process 1, but you can just read this as a number, a real number. Okay, and here the first event is going to be now 1.2. In the third one, the event is going to be 1.3. Okay, so even though none of those events are actually ordered based on happened before relationship, now you can take 3 events, all of which had logical clock value 1, and you can order them, because 1.1 is less than 1.2, which is less than 1.3. So you just imposed a tie-breaking rule. Okay, so it's an arbitrary rule that doesn't actually mean those events actually haven't happened before relationship, but we just converted a partial order into total order. Now we can actually compare any 2 events, and there is going to be an order even if their logical clock values are identical. Okay, but the Lamport's clock is still going to hold, because as you can see, whenever there's an event that's going to go from one, or rather a message that's going to go from one process to the other, you're still going to take the max of the 2 plus 1. Okay, so the send and the receive are always going to be ordered. As you can see, 4.1 is the send, 6.2 is the receive, here 2.3 is the send, and 4.2 is the receive, and so on. So all of the previous properties are still there, and you had imposed a arbitrary tie-breaking rule to order every event. Okay, so you converted a partially ordered set of events into a totally ordered set of events. Okay, so if you use this type of property, you can now take real world examples of distributed applications and use Lamport's clock. And whenever there are events that are concurrent, you can order them. So you get a total ordering. And whenever there's message passing, you automatically order them using logical clock. Okay, here is an example of one such technique or one such application of the Lamport's clock technique. So the example here is there are 2 replicated databases. Okay, so those disks are databases. They're replicated in 2 locations. Okay, maybe it's for fault tolerance reasons. So if one goes down, the other is still there, and so on and so on. Okay, so now because they are databases and you are making queries on these databases, you go modify the database. Okay, so the idea is because they're replicated, every query is sent to both copies. Okay, so if I say, I want to make a buy transaction similar to what you did in lab 1, you will basically send the buy transaction to both the databases, and both of them will actually update. So long as they are synchronized and you execute the same queries, they always stay in sync with each other. Okay, now the problem is if you have queries that are being sent in parallel, you can have a scenario where user 1 sends the query to both databases, and the user 1 is geographically closer to the first replica and further away from the second replica. So his or her query arrives first at this replica and takes a longer network latency to reach the second replica. Okay, and then the second user who's trying to do the same thing. Okay, they are issuing a query, but they are closer to the second replica, so their query appears here first and appears here second. So now you are actually executing the queries out of order. The queries are issued more or less at the same time, but because the propagation delays are different at different replicas, one query arrives first at the first replica, whereas another query arrives first at the second replica. Okay, so if you now execute this query out of order, you will get inconsistent results. Suppose you are buying the same item and you have only one item in stock. So one query should fail and one should succeed if both of them are trying to buy the same item, and you will have different results in this case in different databases, which is not what you want. Okay, so you want to order them and make sure this will not happen. So if you use Lamport's clock to order them, you will always execute queries in the order that Lamport's clock tells you. Okay, so that's an example of how you would apply these types of techniques to databases. Later on in a few lectures, we'll see other techniques like Paxos that try to do this with failures. Okay, because Paxos, this idea is referred to as the problem of agreement or consensus, where you want to agree on an ordering. Okay, here we're trying to agree on ordering of requests that are coming in. Okay, we'll come back to this, but this is probably a very simple way to address it without any failures and so on. Okay.
But does this mean that user 1 has all the priority, or he
Question, does it mean the user one has a smaller priority because it has a smaller number? That's not the case. Okay, this just happens to be a case where the queries were issued concurrently. If user 2 issued the query well before user 1, their query would execute first, because that's.
Yes, but I mean that, of course, if they are sending out of the same order, then there is no problem. But I mean that if conflict, user 1 always has the upper hand.
Right. So the question is, if you have queries being issued at the same time, our tie-breaking rule is the one with the lower process ID wins, because we added process ID as a tie-breaker rule. So if user 1 has a lower process ID, okay, they are going to win. Okay, that we don't decide who gets what ID, but you will assign an ID. But that's a tiebreaker rule. You could assign some other tiebreaker. But yes, in this case, we are using process IDs to break ties. Yes, please. Okay, question is there a reason we don't have 2.2? Is that your question? Okay, so that is exactly the reason how the Lamport's clock algorithm works when you send and receive messages, right? So what is going to happen? This message is going to send, always when you send a message, you piggyback the logical clock value, right? So the message will have this actual message, but you're going to piggyback 2.1 with that message, okay? That message is going to come here, okay? Then you're going to essentially take the max of your local clock, which is 1.2 and 2.1, and that gives you 2.1, and then you add 1, and then that gives you 3, right? So you're essentially doing the max plus 1, which is why you got 3 there. So you will skip over some IDs, which you will see here too, right? Because in this case, you sent 60, so this became 61, and so on and so forth, right? So it doesn't have to be sequential. Okay, any other questions here? All right, so now, so I'm not going to go into this algorithm because I already mentioned how it works, right, in that previous picture here. So we'll skip this for now, but it's essentially the same idea with a little more detail. But instead, we'll talk about vector clocks, which are going to help us with that problem where we want, if A happened before B, timestamp of A is less than timestamp of B. And if timestamp of A is less than timestamp of B, you're guaranteed that A happened before B. Okay, so how are we going to do this? So this requires that we have to generalize the notion of a Lamport's clock. And we want to get a property called causality. Okay, so essentially causality says that there's a causal dependence between two events. Okay, essentially, what is the causal dependence? There is a message that goes from one process to the other. That may be a request, that may be something, some type of message where the other process acts on that message. So hence all subsequent events are going to be determined based on whatever has happened because of this message. So essentially, sending and receiving of messages introduces causal dependencies. Okay, and we want to capture that causal dependence. So we want to essentially maintain causality. Okay, so the very simple definition of causality is if A happened before B, A is causally related to B. If they are local events, then since you're executing them in order, clearly previous instructions have some bearing on what happens next in the process. The sending process is the same thing is true. Okay. Now, there are other causal properties which we will not address with logical clocks, but we'll get to later on. Okay, another one is called causal delivery. Okay, causal delivery says if the send of a message happened before a send of another message because of some message exchange between those processes, then the receive should be in the same order. Right? If there are two events that are causally ordered, if A happened before B and A and B are both sending of the messages, then causal delivery says you should deliver them in that order. Okay, so that gives you additional properties, which we will talk about later. But for now, let's just see how to get the reverse property. Timestamp of A less than timestamp of B. How are we going to ensure that A happened before B? Okay. So this gets us to this notion of a vector clock. Okay. So now we are going to generalize this logical clock algorithm. The same algorithm, but we are going to generalize it. So instead of logical clock was a single integer that a process kept. Okay? Just a single integer, one integer that you kept incrementing on every event. Now, if there are n processes in the system, you are going to, each process is going to keep a vector of integers. There'll be n integers you keep. Okay? So essentially that integer says, so you have n processes. Every process now keeps n integers rather than a single integer. Okay. So what does that vector mean? So the ith, so if your process I, the ith element of that vector is effectively your Lampport's clock. Okay. So if you have 3 processes, okay, so for P1, the first element of the vector is its logical clock. For P2, the second element is its logical clock, and so on. So you are essentially using the same logical clock algorithm. Okay. Now, what do the other elements of the vector mean? The other elements of the vector represent what does process I know about what's the most recent event that has happened at process J. Okay. And this is based on sending of the message. Okay. And we'll try to understand what this actually means. Okay. So rather than explaining this text, I'm going to explain with a figure, and then you can understand what all of this means. Okay. So let's take 3 processes. Okay. So this is P1, P2, P3. Okay. So vector will have 3 elements. Okay. So you always start with 0, 0, 0. Okay. First thing is what will happen if there is a local event. When there's a local event, you increment your element in the vector clock. Okay. So let's say there is a local event at P1. What will that vector clock become? Should become 1, 0, 0, because you are now incrementing the first element, right? So here you will have 1, 0, 0. Okay. If there's a local event at P2, what's going to happen? Okay. It's going to be 0, 1, 0. Right. So and so on with P3. You will basically, so whenever there are local events, you tick your ith element if your process I. Okay. That's all. Nothing happens to the other elements. Okay. Now, if you want to send a message, what do we do? So let's say you send this message. Okay. Like before, when you send a message, you're supposed to piggyback your vector clock. In this case, the vector clock. So you send the message, but you'll also piggyback. In this case, you're going to piggyback 1, 0, 0. Okay. Now, when the message arrives here at the other process, you are going to take the 2 vectors, your vector and the vector that has arrived. You are going to do element by element max, because you're still going to do a max. In the previous case, you did max of 2 integers. Here you're going to do max of 2 vectors. Okay. So what does max of 2 vector means? You compare each element and then you take the max of the 2. So in this case, you compare 0 and 1. So the max is 1. Okay. Then you take the second element. You say, I take the max. So once you do the max, you also tick your local clock, because you always take your local clock when there is an event, because you said max of the 2 plus 1 in logical clocks. Here you do max of the 2 vectors plus 1. Okay. So what will this receive event get as the timestamp? 110. Well, you have to do 110 plus 1 for your thing. Right? So you are going to do 120, because when you do the max, you get 110. Then you increment your element, so you are going to get 120. Okay, yes, question. Okay, so question is, if send is an event, shouldn't it become 2? I just assume that that's the first event that has occurred, right? So if there was some other event, you would have made it 2. You're right. If there was an actual local event, it would have been 2, but I just assumed that was the first event. But yes, of course. All right. So now you can send this message again, and you will do the same max plus 1 and so on. Okay. So essentially, now if you look at, let's do another example, and then let's say here you are now up to 0, 0, 3. Okay. So there have been some events. So you're up to 0, 0, 3. So you get this. So you have 1, 3, 0, and you do a send. Okay. So what will be the clock here? It should be 1, 3, 4. Right. So you're going to take max of 130,003. That gives you 133, and then you increment your clock, so it becomes 134. Okay. So now you can look at the vector clock and try to understand what the elements of the vector mean. Okay. for in the vector clock, the ith element essentially is your logical clock. So that shows how many events have occurred in your process. Because for every event, you are incrementing it. Okay. Now, what do other elements mean? Other elements actually say what is the latest event this process has seen from the other processes. So if you look at 3, okay, in this 1, 3, 4, if you look at the second element 3, okay, that says process P3 knows about local event 3 in process 2, because that was the send event. That's why this became 3. Right? If you look at 1, what does this tell you? Process P3 knows about event 1 in P1. Okay? Now notice that P1 never sent a message to P3, but it indirectly knows about this because the P1 sent a message to P2, and that was local event 1, and P2 sent a message to 2. So essentially through this sequence of messages, now you know something about other processes in the system. Okay? So each element is tracking what is the most recent event you heard about from some other process, either directly through a message or indirectly through other processes based. So it's the most recent send event that you know about from other processes. Okay. So your vector clock is now tracking not just how many events have occurred locally, it also tracks what is the most recent event at every other process that you know about as a result of message passing. Okay, that's the intuitive idea behind a vector clock. But now let's ask the question: does this vector clock actually give us that property we want? If I give you 2 arbitrary vectors, can you say that something has happened before something else? Okay. First, let's just look at the picture and try to reason about it, right? So let's take that send event in process P1, and let's take the receive event in this process P3. Okay. How are they ordered? Do they have a happened before relationship, or are they concurrent? Without looking at the vector values, I just wanted to see the message exchange and try to argue for it. Okay, hold on. Just 1 second. I think the Zoom is not working. Yeah, just. Okay. All right. So the question is, what do we know about that send and this receive? So let's do the simple happened before. Send of that message happened before this receive. Okay, send. Okay, and because these 2 events are local, this receive has happened before that send, and that send has happened before this receive. So by transitive property, that send has happened before that receive. Okay, just by looking with no vector clock, you're just looking at message exchange and just reasoning about the event chain. Okay, now let's look at the vector values 1, 0, 0, 1, 3, 4. Okay, you compare them. Okay, which vector is greater? The second vector should be greater. Okay, but you should ask, what do you mean by greater? Okay, you know, when you compare integers, you know what A is greater than B means. But what's the greater than relationship for vectors? Okay, so we can define that. Okay, you will say that vector V1 is greater than vector V2 if every element of V1 is greater than or equal to every element of V2, and there is at least one element which is strictly greater. Okay, so you will say if some vector is greater than the other vector if all the elements are greater than or equal to the other element, but there's at least one element that's greater, which is true here because 1 is equal to 1, but 3 is greater than 0, 4 is greater than 0. So all the elements here are greater than or equal to all the elements there. Okay. So that is our happened before relationship. So you can do some examples and convince yourself that if you can see any happened before relationship, that is always going to be the case. Okay. Now let's take another example here and say you have another event here 1, 4, 0. Okay. So now let's compare 1, 4, 0 with 1, 3, 4. Okay, so which vector is greater than the other vector? Okay, you cannot compare these two vectors because in this case, some elements of one vector are greater than the other, and some elements of the other vector are greater than the first. So in that case, there is no greater than relationship defined. Okay, greater than relationship is only true if all elements are greater. If you have some elements greater there, some elements greater there, it's undefined. Okay, so we will say neither is this vector greater than that, nor is that vector greater than this. Okay, so what does that tell us? They are concurrent events. So by definition, if you look at this event and that receive events don't have a happened before relationship. So you should not actually have the vectors be greater than or less than. They should be not comparable to begin with. Okay, so you will see that when events are concurrent, okay, if you look at the diagram, you will see when events are concurrent, they are not comparable. 0, 1, 0 is not comparable to 0, 0, 3 because those two are concurrent events. When events are ordered based on the happened before, the vectors actually get ordered. Okay, so as a result, now you can simply look at the vector values, and if there's a greater than relationship, you are guaranteed that those two events are actually ordered by happened before. And if the vectors are not comparable, you are also guaranteed that the events are concurrent. Okay, so this has now given us the opposite property that was missing in logical clocks. Okay, is that clear? Of course, I didn't prove that, but you can at least from the example try to get an intuition that you will actually now get the same thing other way around. Okay, now going back to the other Lamport's clock, you will see in Lamport's clock, if I just compare two integers, that doesn't tell me anything. If I say 80 and 72, of course, numerically 80 is greater than 72, but it doesn't tell me in this case the two events are actually concurrent. It doesn't tell me that, right? So there are arbitrary cases where there will be concurrent events, which if you compare, you will actually get the wrong information, but that will not happen in vector clocks. Okay, if there are two concurrent events, the vectors will not be comparable. But if you have two integers, you can always compare them. So that is why this does not give you the property you want, the opposite property. Okay. All right. So that is vector clocks, and you can see now the vector clock algorithm. It says if there's a local event at process I, you increment the ith element of that vector. Okay. When you send a message, you piggyback the vector. Same thing in Lamport's clock. When you receive a message, you essentially do max of the two vectors, and then you add one to the jth element. If you have process J, it's the same technique that we used in Lamport's clock, except that now you're doing these operations on vectors, not integers. Okay, and just by doing that, now you actually get the opposite property, which I have not proved, but I just showed you with an example. Okay, but you can go back and reason about this a little more and convince yourself that that's always true. All right. Okay, so what can we do with this kind of information? You can essentially enforce something called causal communication. You can enforce causal delivery and so on. So an example is shown in this picture here, where you have three processes, P1, P2, P0, P1, P2. They are sending messages. And in this case, the messages are being broadcast to all processes. Every message is going to every process. It's not a message from one process to the other. You will see every message, P0 sends a message, it goes to both P1 and P2, and P2 sends a message, it goes to both of those, and so on. Okay? Now, if you want to essentially do causal delivery, that's the technique I was talking about. So if the send of two messages is ordered by happened before, you can use vector clocks to enforce that delivery is also going to be made in that order. And that's an example that's shown here. So let's say you send this message, it has vector clock 100, it reaches here, okay, to process P2, and then later on P2 sends a message to other message. So this send and this receive and that send are causally ordered. I mean, that's happened before relationship because they're local events. Okay. Now this message goes. Okay, and now let's assume that because the network delay from P0 to P3 is long, the first message is still in transit. It hasn't reached. Okay? But the second message arrives here. Okay? In the second message arrives, P2 says, okay, I see it has a timestamp 110. So P1 must have sent a message. And since all messages are being sent to everyone, I still haven't received it. Okay? Because now you know that there is actually at least one send at P1. The only events we are tracking here are sending and receiving. There are no local events in this toy example. So you can say, okay, there is a message in transit somewhere. So I'm not going to take delivery of that message. I'm going to wait for that other message to reach. So you will see that it reached here, but you paused delivery. And then this other message came. Okay? And then you took delivery. Okay? Because these two sends are now causally ordered. So the receives also got causally ordered. Okay? Is that clear? This is a simple example of how you can use vector clocks to enforce causal delivery as well. Is there anything I should explain here? Okay, so the basic idea is if two sends are ordered by happened before, the receive is also. So in the basic idea here is this send and this send have a happened before relationship because there's a message that's going this way. So this has happened before that, that's happened before that. So these two sends have a happened before relationship. So the receive of those messages should also have that property. Because if one send has actually happened before the other send, you don't want the messages to be received out of order. Okay? Yes, question? Okay, the question is when process P1 is sending, why is that not 1, 2, 0? I think based on the algorithm I defined, this should have been 1, 2, 0. Okay, so the vector clock property also holds if you don't do this last step. If you just do the max, it still holds. Just to make things clear, we do the max plus 1. Okay? In the book that I took this example for, this step is omitted. It was just doing the max, okay? Which is why I didn't have it. But if we strictly use this property, this will become 1, 2, 0 because there is that will be right. So because you're going to tick the clock, so that will be the second event. So you are right. But that is actually taking a slightly different variant of the Lamport's clock algorithm, but it doesn't change the property. But I will put a note saying this is using a slightly different variant. Otherwise, those clock values don't make sense. Is there a question?
Yes. So the question about page 3 is saying that should the update be Vj of j equal Vj of j plus 1?
What's the question again?
So the question is actually asking about the equation.
Oh, this one.
From below. Yes.
Yeah.
So also Vj of j equals Vj of.
Oh, yes, of course. I made that's actually an error because if you are updating the vector at process j, you update the jth element. That's a typo there. Okay, so this should be Vjj equal to Vjj plus 1. Okay, so that's clearly a typo. Okay, I will fix that and update the posted notes, but yeah, that is certainly a problem. Okay, so vector clock gives us that property. So we are going to stop with vector clocks. And then, so now we learned about logical clocks, we learned about vector clocks. We are going to use them for something, okay? Because these are just abstract techniques that just allow us to order events and so on. What do you do with this? Right? So we'll now start looking at variety of algorithms, some of which we go back to vector clocks and logical clocks and so on. Okay? Now, this one doesn't actually use necessarily the technique, but let's try to understand what the next problem is. Okay? So our problem is one where we want to take a distributed snapshot of a set of processes that are part of a distributed application. Okay, and why would you want to do this? Because let's say you have an application that has n components. Okay, some component fails, it crashes. Okay, now you can restart that component. But what if there were some messages that were being sent to that component that got discarded when when the process had failed? Okay? So if you want to capture, not capture, but ensure that the distributed application execute correctly, you want to make sure that you deal with this failure not by just doing some trivial restart, but you want to make sure that nothing is getting lost. Okay? So to do this, what you will do is you will periodically checkpoint the process. Okay, so what is our technique to do failure recovery? Let's say you had single, I'll explain that with a single process, then we'll see how to do this for a distributed application. For a single process, if you want to ensure that you are fault tolerant, every so often you are going to write your state to disk. Okay, and then continue execution. And if the process crashes, you load the most recent checkpoint and you continue from that point. So that assumes that you don't have to restart the computation from beginning. Okay? Let's say you are doing some long running simulation, right? Let's say it takes 10 hours. After 9 hours, your process crashes. If you hadn't saved state, you would have to restart from the beginning and repeat those 9 hours. But if you every 1 hour, you actually save your state. And when you crash, you just roll back to the previous checkpoint and continue. Okay? So this is a standard technique that is used in fault tolerance to ensure that you can restart a computation without having to roll back to the very beginning. Okay? Now, it's simple to do when there is only one process in the system. But if you have a distributed application where there are n processes that are communicating with each other, taking a checkpoint is a bit harder. Okay? You want that you take a checkpoint in a way that is actually consistent. Okay, so what does that consistency mean? Okay, and we'll define that and we'll see how to take a snapshot in that scenario. Okay, so first I'll define this notion of a state. Okay, so when you checkpoint, you want to capture that state. So we'll define this notion of a global state. Okay, a global state of a distributed system will be defined to be the local state of each process. So that's the state of that process. Okay, plus all the messages that are in transit. These are the messages that have been sent but haven't been received. So they're somewhere on the network being transmitted. Okay, so that's our definition of a state. So when we snapshot the process or we checkpoint the process, that is what we want to capture. We want to capture the local state of every process, but we also want to capture messages in transit so that if you restart the computation, those messages are going to get replayed and nothing is lost. Okay, you don't want messages to get lost. That's the point we want to make. Okay, so then the question is, how do we do this? Okay, so first thing is, if you have a perfectly synchronized clock, this is trivial to do. Okay, so let's say all the clocks on all the machines are perfectly synchronized. Okay, so we'll say at every hour, everything pauses. Okay, it's noon. Let's pause all n processes. Let's then checkpoint them. Let's also capture any messages that are in transit, call socket buffers, etc., etc. And then you're done. Then you resume. Okay. So if you had a perfectly synchronized clock, then taking a snapshot says, because we have to coordinate the snapshot. But that's the whole point. Right? Now you know that even with all of the clock synchronization techniques that we saw last time, there is no such thing as a perfectly synchronized clock. There's going to be some error. Okay, so when you say everybody pause at noon, there is no such concept because all the clocks are a little off with one another. Maybe there's 100 millisecond drift because even NTP is going to give you some error. Okay? So you cannot actually do what I said, right? Because there is no such thing as a perfect clock synchronization. Okay? So if you don't have perfect clock synchronization and you try to do this, then you're going to have some problem where you say at noon, let's take a checkpoint. Processes will pause at slightly different times from noon because they're a little bit off from real time. Okay, they may be a little bit faster or slower, their clocks. Okay? So that means that you're taking checkpoints at slightly different times because your noon is maybe a little bit faster or slower than real time. Right? So that is going to give us some notion of inconsistency if you do this. Right? So the question is, how are we going to get a consistent state even when you have problems with synchronizing clocks? Okay. So the problem only comes because there is no such thing as a perfect clock synchronization. Okay? So to do this, we are going to essentially eliminate the notion of a clock altogether. Because there is no clock synchronization, let's derive a technique that is independent of actual clock synchronization. Okay? So we'll assume that there is, each process is independent and there is no global clock. There's no master clock. There is no clock synchronization at all. Yet we want to take a consistent snapshot. Okay. How are we going to do this? Okay. So to understand that concept, we'll first try to dig a little bit deeper into what it means to take a consistent snapshot when there is no perfect clock synchronization. Okay, so here is a process. Here's a distributed application. There are three processes: P1, P2, P3. X-axis is time. They're doing some computation. There are some messages going back and forth, and so on. Okay, and we want to take a snapshot that is consistent. Okay, now if there was a perfect clock synchronization algorithm, you would pause all of them at exactly the same time, and then they would take a snapshot. So you will have a vertical slice saying that's the point at which I took snapshot. Okay? But now the clocks are no longer synchronized. So we will still say, okay, every hour or at noon, take a snapshot. But you will see now the snapshot is actually happening at different points in time, because that is noon at P3, that's noon at P2, that's noon at P1. So they're slightly offset from each other. So the actual time at which they think it's noon is somewhat different. So they'll take snapshot at slightly different points in time. Okay? Yet we want to ensure that that's consistent. How do we do that? Okay, for a consistent, so first of all, what the dotted line is called a cut, because that's basically the points at which you take a snapshot. That where the dotted line intersects with the process is the time at which you take a snapshot. We'll call it a cut, and we'll say cut is consistent. Okay? If all messages that you have are such that either the send and receive events are before the cut, or both the send and receive events are after the cut, or if the message crosses the cut, the send has to be in the before part and the receive has to be in the after part, then we will call it consistent. Okay? So in this case, M1 is a process where both the send and receive are to the left of the cut. They're before the snapshot altogether. Okay? M2 is a process where the send and receive are clearly after the cut, because that's where you're taking the snapshot. Okay? M3, on the other hand, is a process that is a message that crosses the cut, where the send is before the snapshot and the receive is after the snapshot. Okay? In our mind, that is still consistent. Okay? And M3 in particular is a message in transit. Okay? At the time of the snapshot, the message was already sent, because that send is before the cut, but it hasn't been received, because in the process that continued execution, the receive would have happened sometime after the snapshot is taken. So it is somewhere in transit. It's been sent, but it hasn't been delivered yet. Okay? And we want to preserve that message also as part of our snapshot, because if that process crashes, you are going to restart it from the cut. Okay? If you did not preserve M3, then you will see if P2 starts executing from this point on and M3 is never delivered, there is something wrong, because if there was no crash, that receive of M3 would have occurred in that distributed application. Okay, so you want to take the local state of every process, and you want to take all the messages in transit and save them on disk, and then you replay them. That is called a consistent cut. Okay? So every message in transit essentially will have the send before the cut and the receive after the cut. Okay? That is consistent. Here is an example where it's not consistent. Okay? You will see M2, because the way the cut has been defined, M2 is a process where the send is after, but the receive is here. Okay? Essentially, this process's clock runs slow, so it takes a snapshot at this point after it processes M3. This process's clock is running fast, so it takes a snapshot here before it has even sent the message. So it thinks noon is here, this thinks noon is here, okay, from a snapshot perspective. So what has happened as a result of this? Okay? You have already processed M2 as far as P3 is concerned, okay, because that is where you took a snapshot. You processed M2 and then you took a snapshot. On the other hand, P2 has taken a snapshot here. It hasn't even sent M1, or rather M2. Okay? So if you basically restart that computation where the cut occurs, what is going to happen? You will send M2 again, right? Because P2 is going to start from this point on. It will send M2 again. Okay, since P3 has restarted, it will receive another copy of M2. And that will be inconsistent, because if, let's say, this process was that message was add $100 to someone's bank account. Okay, let's say it's a banking application. Okay, as far as this cut is concerned, you already processed the message, you added $100. Okay, but when you restart P2 here, okay, it's going to send that message again, and that message will be processed twice, and you will get an inconsistent result. So you don't want this to happen. Okay? In this case, it happened because the receive is to the left and the send is to the right. That's not what you want. You always want cut where the send is to the left and the receive is to the right, if there is a crossing at all. There's no crossing of the cut, you don't care. They are both on one side or the other. Okay. So that's the meaning of what is consistent and what is not consistent and why it's not consistent. Okay. This is not a technique, it's just an example. You still have to decide how the technique is going to work. Is this clear? Okay. Okay. So now we'll talk about distributed snapshot algorithm, and I'll show you how to do this with very simple TCP/IP sockets and nothing extravagant. But before we do this, we should try to understand the intuition behind the technique. How does the technique work? Okay. So the algorithm is called distributed snapshot, okay, because you're taking snapshot in a distributed process. But you can actually take that analogy and try to think of actually taking a distributed snapshot. So by snapshot, I mean, in this case, I mean a photograph. Okay. So let's say that you're trying to take a picture of the sky with the camera. Okay. And let's say the sky has some cloud, there are birds flying around and things of that sort. Okay. But let's assume that your camera does not have a field of view where you can take the entire sky with one photo. Okay. So now if you want to capture the sky, what is the best you can do? You can say, I take multiple pictures and I stitch them together. Okay. I'll take a picture of this part of the sky, I'll take a picture of this part, I'll take a picture of that part, and I stitch it together. Then I see the entire sky as a collection of photographs. Okay. But now I say that I want to do this in a consistent way so that I capture the state of the sky as it occurred at that point of time. Notice that I'm taking pictures at slightly different points. I can't take 3 pictures at once. Okay. So I'm going to take a photo here, I'm going to take a photo here, I'm going to take a photo here. So what does consistency mean in this case? All the objects that were in the sky should appear in at least one photo. Okay. No object should appear twice. So let's take the example of a bird. Right? Let's say I take a picture here, there's a bird flying that way. Okay, I take a photo, the bird is here. Then I go point the camera here, I take a picture again, the bird has already appeared in the second photograph. Now I have actually, if I look at the collage, it will look like there were 2 birds in the sky, but there was only one. So that's inconsistent. Okay. The opposite could also be true. I take a picture here, there's a bird flying the other way. Right? So I take a picture, there's no bird in this picture. When I point the camera here, the bird has gone out of the field of view, come to the previous one. So I take a picture here, it looked like there were no birds in this case. That's also inconsistent. Okay. Birds in this case are messages. You neither want to lose a message, nor do you want the message to be processed twice. Both are going to give us inconsistent results. Okay. But if you capture it in a way where you capture all the objects that were in the sky, and every object is only one photograph, and you put it together, then you have a consistent view of what the sky had, even though you took the pictures at slightly different points in time. Okay. Exactly the same idea is true for taking a snapshot of processes. You capture their local state, and then you also want to capture all the messages. You don't want to lose any messages. You don't want a message to be processed twice. Okay. Then we have something called a consistent snapshot. The question is, how do we do this? So here is a simple technique that is going to tell us how we will do it. I think there's a picture here, but let me explain the technique, then I'm going to give an example. So we'll assume there are n processes. Okay. Any process can decide its time, n processes in the application. Okay. Any process can decide its time to take a snapshot and initiate the distributed snapshot algorithm. Okay. So what do you do when you initiate a snapshot? You are going to take your local state, which you take your memory contents, write it out to disk. Okay. So now you saved your state, but you also have to save messages, remember. So what you will start doing is, you will, let's say you have some socket connections to other processes. Okay, they are simple TCP/IP socket connection. You are going to send a special packet called a marker packet on that socket. Okay, so in addition, normally you would send real messages. You will send a special message called a marker. The marker is an indication to the other process saying take a snapshot. Okay, so you're going to, so every process or any process that initiates the algorithm first writes out its state to disk, and then it sends a marker on all of its outgoing socket connection or any socket connection, because they are by definition outgoing. Okay. Now, if some other process on its socket receives a marker message, okay, and it will, if it is the first time it has received a marker, then it will say, okay, it's time to take a snapshot. Okay, some process has initiated one. Here's a marker that says, marker is a message that says take snapshot. Okay? So you will basically say, okay, time to take a snapshot. So I write out my state to local disk, and then I repeat. I send markers to all my outgoing connections saying take a snapshot. Okay, and the other thing you're going to do is as soon as you take a snapshot for the first marker and you send these messages out, you also start recording all the messages that are coming in because they're all messages in transit. Okay, so on all my incoming channels, I start saving messages until I receive a marker message on that channel. Okay, so that's the technique, but I'm going to draw a small picture to show what this actually does. Okay, so let's go here. And then, okay, so here are 3 processes. Okay, so I'm going to take each socket connection and draw 2 arrows. All socket connection or TCP/IP connections are bidirectional, but I'm just going to show them as an outgoing channel or outgoing and incoming channel. Okay. Okay. So let's say this is process 1, process 2, process 3. That's your disk. That's your disk. That's your disk. Okay. Process 1 starts the snapshot. It says, let's time to take a snapshot. Okay. So it's going to take its contents and write it out to disk. Okay. So what is it going to do? It's going to send a marker message on its outgoing channel. Okay. That's a blue message. Okay. Blue message means take a snapshot. Okay. So essentially that message is going to go on that channel. Eventually it's going to hit 2. Okay. When 2 gets that marker message, the blue message, it says, okay, I got an indication it's time to take a snapshot. The first time it's received that marker message. Okay. So it's going to write its content to disk. I should have been black. Okay. And it's going to send marker messages on its outgoing channels. Okay. So here is one that is going to send, and here's another one it's going to send. Okay. Is that clear what I just did here? Okay. Now, when you take a snap, when you write out your memory state and you send markers on your outgoing channel, you have to do one more thing, which is you have to save all messages that are coming on your incoming channels until you get a marker message on those. Okay. So one in particular, after it wrote its memory state to disk, is recording all messages that are coming on its incoming channels, which is this channel and that channel. Okay. So incoming messages will put in red. So we'll assume that there are all these red messages coming in incoming. So all of those also get saved to disk. Okay. So you're going to write that memory state and you're going to write all these red messages. Okay. Until you get a marker message. So in this particular case, one which initiated the snapshot and sent those marker messages is going to write these 2 red messages to disk, is going to write some other red messages from 3 to disk and so on. Those are your incoming messages. Okay. So now 3 is also going to either get this marker message first or that marker message, because there are 2 marker messages transit. One of them is going to arrive first. Then it's going to say, okay, time to take a snapshot. So it will write out its memory state to disk, and it's going to send marker messages on its outgoing channels, which are here, right? And it's going to wait for incoming markers on any incoming channels. Okay. So if it processes this incoming first, then it will wait until that one comes and stop recording. Okay. So as far as 1 is concerned, it's recording all incoming channels. You'll see that a marker message does arrive on every incoming channel, and then it'll stop when it's done. Is that clear what I said? So just to repeat again, any message, any process can initiate a snapshot. The way you start the snapshot is you write your local state to disk, you send marker messages on your outgoing channel, and you start recording all socket messages coming on your incoming channels. Record means you keep a copy on disk. Okay. And you keep recording until you receive 1 marker message on each of those channels. Any process that receives the marker for the first time recursively does the same thing. Okay. It says, okay, time to write local state to disk. Let's send marker messages on all outgoing connections. Let's record all the incoming messages until a marker message is arrived. And that is going to give you essentially a distributed snapshot. Notice here that things are happening at different points in time. We didn't say it's noon, clock is synchronized, all processes pause, time to take a snapshot. All the processes took snapshot at different points in time because they're not synchronized, yet it is consistent because it saved the local state of every process. Every message in transit has been captured because those are the messages that were coming on the incoming channel after a snapshot was taken. Okay. Is that clear what I'm saying here? Okay. Now, the thing that you have to convince yourself is that you actually captured all the messages in transit. Okay. That is the part that may not be apparent. Okay. So in particular, messages like M3 have to get saved. And if you actually construct this example, you will see that that is exactly what is happening. Any questions on this? Yeah, so here is an example which is showing only one, because there's another one here, which is showing the same thing, where Q decides to take a snapshot. Okay, so it's going to write its state to disk, and it's going to start send markers on outgoing channels, and it's recording its incoming channels. So it's going to say A, B, C, here D, and then a marker comes, and then essentially it's saved its memory state. It saved A, B, C, D are the messages on its incoming channel until a marker arrives. Okay? This is showing the same example with only one process. I showed you the example with 3 processes. Any questions here? Your question? I'm sorry? Right. That's exactly right. A marker, the first marker says start recording. Okay. And then all the incoming markers tell you stop recording. That's what it is. Right. The first incoming marker always says start recording. And then you start recording all your incoming channel, and all subsequent ones tell you stop. That's exactly what it is. Yes. Any other questions? Okay.
So is this guaranteed to be correct? Because there are, like, I can think of multiple scenarios that this can go out of sync.
Okay. Question is it guaranteed to be correct? This is guaranteed to be correct under one assumption, which is that all my channels are TCP/IP sockets. Okay. And you are delivering messages in order. Okay. Under that property, this is guaranteed to be correct. It doesn't matter whether you have clock synchronization or not. So long as you have, if you do TCP, it's anyway giving you in order delivery. Right? When in TCP, if you send 2 messages on a socket, they are guaranteed to be delivered in order. So the basic idea is, if you are going to use TCP as your way to communicate, this algorithm is guaranteed to be correct, is guaranteed to terminate, meaning that it will stop recording. You can say, why will some process stop recording? You're actually guaranteed that as well. Okay? Or you can ask your questions, and we can try to answer why you think there is a scenario where it may not work. And we can try to figure out why that actually may not be the case.
I was actually did not notice that the assumption that it's using TCP. So I was thinking of other.
Yes.
But if I'm using TCP, why I do not like orchestrate my snapshots in a better way, so that I will only take the snapshot after the messages are acknowledged that it is received.
Okay, question is, if you use TCP, why can I not use TCP to coordinate messages? So this doesn't say that you are precluded from doing some other way of distributed snapshot. This doesn't say it's the only way, just to be very clear. But this is a way which is very simple. Okay, and is guaranteed to give you the property you want, which is it will take a snapshot, and furthermore, if any process crashes, you can terminate them all, and you can restart the process. Okay, so what will restart mean? So in this case, if I restart Q, I start from that point on, and I replay messages A, B, C, D, and you are guaranteed to basically reach the same state at the end. That's all it's telling us, right? And yeah, so but you don't need to coordinate, you don't need to do anything. Can you coordinate and do something else? Sure, there are other snapshot algorithms. That doesn't mean this is the only one. But so long as you don't have out of order delivery, you can't have a marker that jumped over B and got delivered out of order. That will actually destroy this property. But TCP gives that for free. So if you just use TCP, UDP will not give it. So if you're using UDP to communicate, you will not get this property. But if you use TCP, it's fine. Right? So any other questions?
In the distributed snapshot algorithm, the case where the send is before the cut and receive after the cut cannot happen because
Yeah.
in the outgoing channel they are actually waiting for all the receive.
Right. The question is, in a distributed snapshot, this inconsistent cut will not occur where the send is after and the receive is first.
The send is before the cut and receive.
Okay. So question is, in a distributed snapshot, can you actually have a case where the send is before and the receive is after? This is exactly the case where you are going to record M3, right? So because what will happen? Think about process P2. Okay, P2 has taken its saved its local state here. M3 is a message in transit, so it has actually been sent by P1 as far as when it takes a snapshot. So it will keep recording its incoming channels, and essentially it will keep the state will be that will be its local state, and it will save M3 as part of its disk. So that will be a message in transit. Right. So question is, will it not apply? As far as the snapshot is concerned, it's going to essentially receive the message and keep a copy on this. But the process is still executing. So it will apply M3 and do whatever it wants. But that's not part of the snapshot. That's part of the regular computation. You're not going to, just because you saved a process message to disk doesn't mean you don't process the messages. Remember, the snapshot is occurring in parallel to the actual application. Right? So if you send a RPC request saying, buy a thing, you don't say I save the byte to disk and ignore it, because the application is still running, it still has to process them. Okay? So you will process M3 and keep a copy on disk. That's what it will be. Other question? Yes. Okay. Question is, can a process not send new messages before you receive? There is no restriction on what the process can do while the snapshot is occurring. You will receive a marker, you will save your state. You can still send outgoing messages. There's no problem, because they will be your outgoing message is an incoming message for someone else. So long as you have not yet sent the marker, they will record your message. But if you already sent the marker and then send those messages, the marker comes first, so you will not actually record those messages, right? So while you are saving state, if you send some message on your outgoing channel, that's okay. So you can continue, the computation can continue as is. So think of this as you have a separate thread that is doing this distributed snapshot in each process. The other threads are continuing to do whatever they want. Nothing has changed. We just have these special messages that are getting sent that say start recording, stop recording, and so on. Right? So everything else continues as is, and the start and stop will tell you how many messages you want to save. That's it. Okay. So it's a little bit subtle to prove that actually it captures all the messages in transit, but you can do some examples and convince yourself. Okay? Because the algorithm is so simple, it almost sounds like, why does this even work? Because all you're doing is I send a marker, I save my state, I start saving other messages until I receive marker. That's it. You can describe that technique in 4 lines. Okay? But it actually gives us all the properties we want. Okay. So we will do one more thing here, and then we will stop for spring break and resume in 2 weeks. And that one is called, that technique is called termination detection. It is basically like snapshot algorithm, but it's trying to solve. Snapshot algorithm is taking a distributed snapshot. Termination detection is a problem that says, has the computation finished? Okay. Now you might say, why would I need to know has a computation, or why would a process need to know this? So think of a distributed simulation. Okay. In a distributed simulation, you do some local simulation work. But if there are requests coming from other processes that are part of the simulation, you process those messages as well. Okay? And now each process needs to independently figure out, has the simulation done? Is it done? Okay? So maybe you say, I did all my processing. Okay? Should I just quit as a process? The answer is it depends. If some other process is yet to send you a message, then you should stay and wait for that message, and that message might make you do additional computation. But if no other process is going to send you any message, then you're done because you have done your local work. No one is going to send you any more messages. So there's no new work that's going to arrive. So you can quit as a process. Okay. But how is a process to figure out, okay, whether it should terminate or not, or whether the entire computation is terminated or not? Right. So that is the problem of termination detection. Okay. So the way this technique is actually much simpler than the previous one. The way you are going to actually do this is you are going to essentially query all processes saying, I am done, okay, with all my local work. So you ask everyone else saying, are you done with your local work? Okay. If any process says it's not yet done with its local work, then you say perhaps that local work might trigger additional messages. Those messages might come to me, and so I might have to do more work, so I will not quit. But if every process says, yes, they have also finished their local work, then it's clear that everyone is done doing local computation. So there's no new messages they are going to send. As a result, there is no new work that's going to be generated for any other process. Then all the processes can safely quit, and there is no problem. Okay. So it's a distributed way of figuring out, when you finish as a process, finish your local work, will there be more work for you coming after this point or not? Okay. If there's not, then you can quit. If yes, there is a chance you stay and keep listening for requests. Okay. So that's the problem of termination detection. Okay. And once I explain this, it should be very clear how you can do this. You could simply have queried every process and gotten their response. Are you done? Yes, no. If any process says they're not done, then you don't stop. If every process says yes, then you know that everybody's done and all of them can quit. Okay. That entire process is now done not by broadcasting to all processes, but simply sending to any process to which you have an open socket connection. The assumption is all processes are communicating with sockets, so it's a connected graph, right? So you simply ask your neighbor. So you will say, so essentially you can start this termination detection algorithm, and you basically send a done message. And if you are done, you send a done message to all the processes to which you have open TCP connections. Okay, that's like asking, I am done, are you done or not? Okay, so what that process will do is it will check if it's currently executing or not executing. If it is done with its local work, okay, then it is going to ask other processes to which it is connected to. Okay. If it is not done with its local work, it can just say, I continue, I'm not done. Okay, because there's no need to ask anyone. If you know you are still have work to do, the whole computation cannot terminate. Okay, so when you receive a done message, you check your local state. If you are done with your computation, then you say, I'm done, but maybe I should ask my neighbors. Okay, so you are going to broadcast these done messages to your, not broadcast, rather send done messages to your outgoing channels, and you wait for replies. Okay, every process that receives a done message can reply in one or two, send one of two messages back. You either send a done or you send a continue. Okay, when do you send a done? If all your neighbors tell you they are done and you are done, then you send whoever asked you, you tell them I am done. If somebody asked you, are you done? And then you asked your neighbors. If your neighbors all say yes, they are done, you find that you are done, you send a done message. But if one of your neighbors tells you continue, that means that something in their graph is not done. You say, you send a continue back. Okay? So this is just a way of polling every process in your network. Okay, are they done or are they not done? Okay? If there's any subset of processes that are not done, you will get some continue requests back. And then every process will know that there is something yet to be finished, so you will not stop. You will essentially continue to run. But if everybody sends you're done, then this process says, okay, I am done. Everybody has been polled and they said they are done, so there's nothing to be done anymore. So let's terminate. Okay, it's a way to poll more efficient polling than just broadcasting to everyone. Yes, question.
Is there a timeout mechanism here? My question is, so if one of the processes is some idle work and the others will never receive a down message.
So can you explain the scenario? You are asking, is there a timeout and what's the scenario?
For example, we have 5 processes processes.
Yes.
And then all of them are done.
Okay.
And we are waiting for one of them.
Yes.
But one of them is doing some weird work, so it never terminates. So in this case, we have to wait maybe dying. Yes.
No, if it is, so first of all, this does not, so I should explain, the termination detection problem doesn't deal with failures. Okay. If some process is failing in the middle of this is not going to give a consistent answer. Because you ask somebody that they never respond to you. You can't figure out what. So you are assuming that you have an answer only if everybody responds. So this is not being, neither this nor the distributed snapshot is dealing with a case where there are malicious processes that don't record some state. There are processes that are failing in the middle of this. That technique, neither of these techniques will work in that case. So in the distributed snapshot case, if there's a failure in the middle, you go to the previous snapshot that you already taken and start from there. You don't try to fix this snapshot because it's not going to work, right? In the termination detection, if there is a process that has hung, is doing something that malicious, you can send a bad message, right? So of course, you will confuse everyone. So that then this is going to give an inconsistent result. So this technique only works when all processes are correct. Okay? So we have not dealt with the case where if there is a malicious process or a failed process, what happens? So then it will not actually give you an answer or may give incorrect answers. All right. Okay. So I guess that was the last slide for today. We have a few minutes remaining. We will end early here. So we'll resume after spring break. I already sent a message about midterm exam. Okay. The date I had already announced. I announced the classroom and so on. And I put out a sample midterm as a way for you to get some sense of what type of questions to expect. Okay. So we will have discussion of all of that after spring break. So have a good spring break. We'll see you in some a weekend a little bit.